Behind every great result, there is a hidden process most people never notice. Welcome to the channel. Today, we are diving deep into this fascinating world to see how it actually works.
It is easy to assume that the most famous object in astrophysics was discovered by the most famous physicist in history. Pop culture often credits the black hole entirely to Albert Einstein, but Einstein didn't discover black holes. In fact, for decades, he didn't even believe they could physically exist. In 1939, he actually published a paper trying to prove they were mathematically impossible. So if the architect of modern physics flatly denied they were real, who actually found them? And how did they use Einstein's own equations to prove him wrong? The answer reveals something deeply comforting about the scientific method. The math and the physical reality it describes don't require the belief of their creators to be true. To understand this disconnect, we have to rewind to 1915. Einstein had just published the architectural blueprint for how gravity works, the theory of general relativity. He showed that space and time are woven together into a four-dimensional fabric. When you place a heavy object like the sun onto this fabric, it warps the grid, creating a deep dip. When you see other objects like Earth rolling around that dip, you are looking at what we experience as gravity. Einstein had successfully mapped the cosmos, but in doing so, he accidentally wrote the rulebook that allowed cosmic monsters to exist. Less than a year later, a German physicist and astronomer named Karl Schwarzschild got his hands on Einstein's new equations. He was serving on the Russian front in World War I, literally solving the math between artillery calculations in the trenches. Schwarzschild pushed Einstein's math to its absolute extreme. He realized that if you pack an immense amount of matter into an infinitesimally small point, a singularity, the warping of spacetime doesn't just create a dip, it becomes an infinite, bottomless spike. He calculated a precise perimeter around this infinite spike. Cross that boundary, and the gravitational pull becomes so severe that absolutely nothing, not even light, can climb back out. Today, we call that boundary the Schwarzschild radius. Schwarzschild mailed his findings to Einstein. Einstein was impressed by the mathematical elegance, but he completely rejected the idea that such a thing could form in the physical universe. He felt that nature would inherently prevent a star from collapsing that far. By 1939, Einstein argued in a published paper that the particles inside a collapsing star would simply speed up and stabilize long before they ever reached that point of no return. The pure math insisted these infinite gravitational traps were out there, while the man who wrote the original equations swore the universe would forbid them. The debate shifted from abstract math to actual stellar physics later that same year, thanks to J. Robert Oppenheimer and his student Hartland Snyder. Oppenheimer looked at the life cycle of a massive star. A star holds its shape because nuclear fusion generates outward pressure, balancing the inward crush of its own immense weight. But eventually, a star runs out of nuclear fuel. When that fuel is gone, there is no outward pressure left. Gravity wins. It crushes the star endlessly inward, past Schwarzschild's point of no return. Decades later, in 1967, physicist John Archibald Wheeler finally gave this proven, terrifying phenomenon the name that stuck: the black hole. Oppenheimer bridged the gap between equations on a page and physical reality. He showed that the universe has no fail-safes against infinite gravity. Proving they can exist on paper is one thing. Actually finding one is a massive logistical nightmare. Because black holes emit absolutely no light, astronomers had to figure out how to locate a completely invisible object in the dark of space. They realized they had to look at what the invisible object does to its neighborhood. In 1971, astronomers detected intense X-rays blasting from a system called Cygnus X1. An unseen massive object was violently ripping gas off a neighboring star. They had found their first strong candidate. A century after Einstein's original paper, scientists built massive physical tools, like the miles-long LIGO detectors, to test his theories on a whole new scale. In 2015, LIGO didn't look for light. Instead, the highly sensitive instruments physically recorded tiny ripples in the fabric of spacetime itself, waves created when two massive black holes collided. Through these specific indirect observations, black holes transitioned from a highly debated quirk of mathematics into an undeniable, measurable cosmic reality. But indirect evidence left astronomers wanting more. That led to the 2019 effort by the Event Horizon Telescope, a global network of observatories aiming to capture direct visual proof. They produced this image of the black hole in the galaxy M87. That glowing orange ring of superheated gas is framing a dark center. We are looking at the literal shadow of the event horizon that Carl Schwarzschild predicted in the trenches of World War I. When you look at this shadow, you are looking at the ultimate contradiction to Einstein's 1939 paper. We are staring directly at the physical object he swore could not exist. Yet this amplifies Einstein's genius. He built a mathematical framework so accurate and so powerful that it outpaced his own imagination. The math successfully predicted cosmic monsters that were smarter than the man who wrote it.